Hey everyone! In this video, we're going to learn about Newton's first law of motion. We'll cover balanced and unbalanced forces and how to calculate the net force on an object. And then, we'll explore Newton's first law and learn how a net force affects an object's motion. After that, we'll look at some different scenarios and we'll try to explain what's happening using Newton's first law of motion. In the last video, we mentioned that everything we've learned so far has been kinematics, which covers how objects move. Now we're moving on to dynamics, which covers why objects move, or what causes them to move. So let's start this video by trying to answer the question, why do objects move in different ways? Even though we see things moving and not moving all around us, we usually don't think about what's causing those things to happen. Let's look at 6 different scenarios and see if we can explain why the object is moving a certain way. Then we'll come back to these after we learn about Newton's first law of motion. So first, let's say you're trying to slide a box across the floor. You push it as hard as you can, but it still doesn't move. So in this scenario, why doesn't the box move? Pause the video and write down your explanation, or try to explain it out loud, but see if you can come up with a reason before moving on. In the next scenario, you grab a book, slide it across a table with some initial speed, and then it stops. So why does the book stop moving? Now let's say you're watching a hockey game and a player passes the puck across the ice. The puck seems to be moving at a constant speed, and it doesn't stop. If the book stopped on its own, then why does the puck keep moving at a constant speed? In the next scenario, you're trying to move another box. But this time, the box slides across the floor with a constant speed while you're pushing it. And if you stop pushing, the box stops moving. If the hockey puck moved at a constant speed on its own, then why does the box require a push to keep moving at a constant speed? Now let's say you drop a ball from rest. We know from projectile motion that the ball will accelerate downwards, and 1 second later, its speed is 9.8 meters per second. So why does the ball accelerate, and why doesn't it fall at a constant speed? In the last example, a person is riding in a car, and the car is turning quickly around a corner. If you've been in this scenario, you probably felt like something was causing you to move sideways towards the outside of the turn, and you had to lean against a door or hold onto something. So in this scenario, what's causing the person to move sideways in the car while the car is turning? Alright, so hopefully you were able to come up with some explanation for each scenario. Here are some common things that people think of. Objects eventually stop moving on their own, and they naturally come to rest. That might explain why the book slows down and stops. But it doesn't explain why the hockey puck keeps moving. Maybe it just needs more time to stop on its own. Next, objects don't move on their own, and a force is needed to move an object. So maybe there's a force that's pushing this person to the side as the car turns. And maybe that's why you had to push on this box to keep it moving. But if that's true, why doesn't the hockey puck need a force to keep it moving? And does a force move an object at a constant speed, like the box? Or does a force cause an object to accelerate, like the ball? And finally, if an object is not moving, then there are no forces acting on it. Does that explain why the first box isn't moving? The person is definitely applying a force to the box, but it still doesn't move. Even though these statements feel like they match what we observe in everyday life, they're actually not true. But if you used any of them to explain these scenarios, you're not alone. For thousands of years, these are some of the ways that people explained motion. Nobody was really sure why things behaved the way they do. and even the smartest people in every period came up with some theories that sound pretty weird today. Over time, people started to piece things together, and eventually, an English philosopher named Isaac Newton summarized things with what we now call Newton's 3 laws of motion. We can use these laws to explain the scenarios above and pretty much all motion that we see. We're going to cover Newton's first law in this video and the other laws in the next few videos. We need to understand forces in order to understand these laws. And we covered forces in the last video, so watch that one first. But if we look at the first 2 laws, it's not a force that affects motion, it's a net force. So let's explain what a net force is, and then we can learn Newton's first law of motion. The net force acting on an object is the total, or the sum, of all of the forces acting on it. And remember, forces are vectors, so the net force depends on the magnitudes and the directions of the forces. We can write net force like this, but we're usually going to write it like this. The Greek letter sigma means the sum of multiple things, so sigma F means the sum of all the forces, which is the net force. So in the examples below, what is the net force acting on each box in the horizontal direction? And to keep things simple, let's say there's no friction force on the boxes. Okay, so first, let's draw free body diagrams that just show the horizontal forces on each box. In the first example, the person is pulling the box to the right with 10 newtons of force. Remember, a newton, capital N, is the SI unit of force. Since the box only has one force acting on it, that's also the net force on the box. So the net force is 10 newtons to the right. In the second example, there's a 10 newton force acting to the right and a 10 newton force acting to the left. In this case, the net force is 10 newtons minus 10 newtons, which is 0 newtons. So there's no net force on this box. We're subtracting one force from the other because they point in opposite directions. And since forces are vectors, we need to account for those directions. We'll cover this more in the next video, but we can think of it like a game of tug of war. The 2 forces have the same magnitude or strength, 10 newtons, and they're pulling in opposite directions, so they cancel out and there's 0 net force. In the third example, a person is pulling to the right with 15 newtons of force, and a person's pulling to the left with 10 newtons of force. This means the person on the right is pulling harder than the person on the left. So now, the net force is 15 newtons minus 10 newtons, which is 5 newtons. So the net force on this box is 5 newtons to the right. We could think of the left force as canceling out 10 newtons from the right force, so we're left with 5 newtons on the right. If the forces were switched, and the left person was pulling harder, then the net force would be 5 newtons to the left. So those are the net forces on each box. A net force is not a certain type of force, it's just the total, or the sum, of all of the forces on the object. For the second box, we would say that the forces are balanced, because the forces on each side have the same magnitude, and the net force is 0. For the first box, we would say the forces are unbalanced. There's only one force pulling to the right, and there's no other force to balance it out. And for the third box, we would also say the forces are unbalanced. There's 2 forces in opposite directions, but the left force is stronger, so they're not balanced, and there's a net force to the left. We'll go into more detail in the next video, but that's all we need to know for now. So we've learned about forces and net forces, so now let's learn about Newton's 3 laws of motion. We'll start with the first law and cover the next 2 in other videos. Newton's first law of motion says that an object at rest will remain at rest, and an object in motion will continue moving in a straight line at a constant speed unless acted on by a net force. There's really 2 parts to this law, so let's split them up and talk about each one. First, an object at rest will remain at rest unless acted on by a net force. So let's say we have a curling stone sitting at rest on some ice. Remember, at rest means the object isn't moving. Newton's first law says that this curling stone will remain at rest. It will continue to not move unless a net force is applied to it. So if you want the stone to start moving, you need to push it with a net force. The second part says that a moving object will continue moving in a straight line at a constant speed, which means its velocity vector will stay the same, unless acted on by a net force. So let's say someone already pushed the curling stone. Once it's moving, it will continue to move in a straight line at a constant speed forever. It won't speed up, it won't slow down, and it won't change direction. If we want to stop the curling stone, we need to apply a net force. And that's usually what happens. Even though ice is slippery, there's still some friction force acting on the curling stone in the opposite direction. That friction is the net force, which is slowing it down, or changing its speed according to Newton's first law. If the ice had no friction, and there was no air resistance, then the curling stone would move at a constant speed forever. Pretty much every object has a friction force acting on it, so it can make things a little confusing when we're trying to learn how forces affect motion. It helps to think about objects sliding on ice with zero friction, but let's go somewhere else where there are no other forces to worry about. Somewhere deep in outer space. The laws of physics work the same way everywhere in the universe. But out here, we can imagine an object has no friction forces because it's not touching any surface. There's no air resistance because there's no air in the vacuum of space. And we'll assume there's no gravitational forces because the object is far away from the Earth, the Sun, and other planets. So this box is free to float around in space, and we can apply our own forces to better understand how they affect its motion. This is really how we want to start thinking about objects, forces, and motion. Instead of assuming an object will behave a certain way, we want to start from the ground up. Imagine the object with no forces acting on it. Then we can add on any forces that are involved in different situations, and then we can figure out the motion from there. But fundamentally, all objects follow Newton's laws of motion, which start with how objects move when there is no net force. So let's say we have a box that is not moving. The box is at rest and it has zero speed. We're assuming that there are no forces acting on the box, which means the net force on the box is zero. According to Newton's first law of motion, this box will remain at rest forever. The only way that it'll start to move is if some net force is applied to it, which we'll get to in a second. But this means that a force is not required to keep an object at rest. Objects remain at rest on their own. Now let's look at a box that is already moving at 2 meters per second. Again, there are no forces and no net force on the box. According to Newton's first law, the box will continue moving in a straight line at a constant speed forever. The net force is zero, so the velocity is constant. The box doesn't speed up, slow down, or change direction. So we can say a force is not required to keep an object moving. You might be thinking, well, why is the box moving? Wouldn't a force be required to get it moving? Otherwise, it would remain at rest. And that's true. There's a subtle difference between those two things that can be confusing. A net force is required to change its velocity from not moving to 2 meters per second. But this box was already moving at 2 meters per second, and Newton's first law is saying a force is not required to keep it moving. This is known as inertia, which is the tendency for an object to maintain its state of motion, or resist a change to its state of motion. So we could say this box will move at a constant velocity forever because of its own inertia, or because it follows Newton's first law, which is often referred to as the law of inertia. So that's what happens when there are no forces involved. But Newton's first law only mentions a net force. So what's another scenario where the net force is zero? Since we're in space, let's add some rocket thrusters that pull the box in opposite directions. In this case, each thruster pulls with the same amount of force, 3 newtons. So what is the net force on the box? It would be 3 newtons minus 3 newtons, which is 0 newtons. The forces have the same strength and pull in opposite directions, so they cancel out and there's no net force. If the box is at rest, then it will remain at rest, and we can say an object at rest may have forces acting on it, but the net force is 0. What if this same box was already moving at 2 meters per second? The net force is still 0, so the velocity is constant. This box will move in a straight line at 2 meters per second forever. Again, it doesn't matter how or why the box was moving to begin with. Maybe someone gave it a push. But it's already moving, and the net force is 0, so it will continue moving with a constant velocity. And we could say that an object moving with a constant velocity may have forces acting on it, but the net force is 0. But what if there is a net force? Let's say the rocket thruster on the right is now pulling with 5 newtons of force. Now, the net force on the box is 5 newtons minus 3 newtons, which is 2 newtons to the right. According to Newton's first law, the box will not remain at rest or move at a constant speed. The net force is not 0, so the velocity will change. It turns out that the box will accelerate and speed up in the direction of the net force, which will be explained by Newton's second law. So if this box started at rest, the net force of 2 newtons will cause it to start moving and speed up over time. Or let's say the net force was acting to the left, and the box was already moving at 2 meters per second. The net force would cause it to slow down because it's in the opposite direction as the velocity. So we can say that if an object's velocity changes, there must be a net force acting on it. When we think of velocity, we usually think of the magnitude, or how fast something's moving. But velocity is a vector, so it has a magnitude, which we call speed, and it has a direction. Newton's first law applies to both parts. The speed and/or the direction will change if there's a net force. We saw how the speed would change, but how would the direction change? That happens if the net force is not parallel to the velocity. So if this box is initially moving to the right and the net force is upwards, the velocity will change direction. Newton's first law says a moving object will continue moving in a straight line at a constant speed unless acted on by a net force. So we can say if the direction of an object's velocity changes, there must be a net force acting on it. So here's a quick summary of Newton's first law of motion. First, an object at rest will remain at rest if there is no net force acting on it. There may be forces, but there's no net force because they cancel out. Second, a moving object will continue moving in a straight line at a constant speed if there is no net force acting on it. Again, there may be forces, but there's no net force. If there is a net force acting on the object, its velocity will change. It might speed up, it might slow down, or it might change direction. While we're here, let's explain why those statements from before aren't true. First, objects eventually stop moving on their own, and they naturally come to rest. Now we know from Newton's first law that objects actually keep moving on their own because of their inertia. If a moving object slows down and stops, it's because there's some net force causing it to do that. Next, Objects don't move on their own, and a force is needed to move an object. Here's where we need to be more specific. Objects continue to move on their own once they're moving, and a force is not needed to keep an object moving. But if we meant that objects don't start to move on their own, then that's true. A net force is needed to get an object moving from rest. So we could say that one's half true. We just need to be specific about the word move. And last, if an object is not moving, then there are no forces acting on it. It's true that an object will remain at rest if there are no forces acting on it, but we also saw that an object will remain at rest if there are forces acting on it, as long as the net force is zero. So that's Newton's first law of motion. It's easy to see how objects move in space when there's no other forces involved. But let's go back to the real world and use Newton's first law to explain the scenarios from before. We still have a lot more to learn about forces, so don't worry if something doesn't make sense yet. So first, if you push on a box and it doesn't move, what's going on? According to Newton's first law, if the box remains at rest, then the net force on the box must be zero. So let's look at a free body diagram of the box and just focus on the horizontal forces. If the person is applying a pushing force to the right, how can the net force be zero? Well, there must be another force with the same magnitude acting to the left. And in this case, that force is friction. For example, maybe both forces have a strength of 30 newtons, so the net force is zero and the box remains at rest. If one force was greater, then the box would start to accelerate. But since it remains at rest, we know that the net force on the box must be zero. In the next scenario, when you slide a book across a table, why does it slow down and stop? According to Newton's first law, there must be a net force acting on the book. After you let go, there's only a friction force acting on the book in the horizontal direction. Maybe it's something like 8 newtons. So the net force on the book is that friction force, 8 newtons to the left. Since the net force is not zero, the velocity changes from 5 meters per second to 0 meters per second. The book doesn't stop on its own, it stops because of the net force. If there was no friction, the book would keep moving because of its own inertia. You might be asking, once the book stops, why does it remain at rest if there's a net force? Well, it turns out that once the book stops moving, there's no longer a friction force. We'll explain that more in the lesson on friction, but now that there's zero net force, the book remains at rest. In the next scenario, why does the hockey puck keep moving at a constant speed? According to Newton's first law, there must be no net force on the puck. If the speed actually is constant, then there's no friction force on the puck because the net force is zero and there's no other horizontal forces. So without friction, the puck will move in a straight line at a constant speed forever. But in the real world, there is a small friction force, maybe something like 0.1 newtons. So there actually would be a net force on the puck, and it would slow down and eventually stop. Next, why does this box require a push to keep moving at a constant speed? Let's say the person is pushing the box to the right with 35 newtons of force. If the box is moving at a constant speed, Newton's first law tells us that the net force must be zero. So there must be a 35 newton friction force, or some other force, acting to the left. The box does require a net force to start moving from rest. Maybe another person helped to get it moving. But while it's moving at a constant speed of 1 meter per second, the net force must be zero. If either force was greater, then the box would speed up or slow down. In the next scenario, why does the ball accelerate downwards? If the speed is changing, Newton's first law says that there must be a net force acting on the ball. And it turns out that the only force is a downwards gravitational force from the Earth, if we ignore air resistance. For a baseball, that force is about 1.5 newtons. So the net force on the ball is 1.5 newtons downwards, which causes the ball's velocity to change. In the last scenario, the car is turning around a sharp corner and the person feels like they're moving sideways towards the outside of the turn. So what's going on? Let's look at this point in time when the car is here. The person's velocity at that moment is pointing in this direction. And Newton's first law says that the person will continue moving in a straight line unless there is a net force acting on them. So if we removed all the forces on the person, they would naturally move like this because of their inertia. But there is a net force on the person from the seatbelt or other forces from the car, so they don't move in a straight line. The seatbelt forces their velocity to change direction, but the person's inertia wants them to be out here. So there isn't a force pushing them outwards, it's their inertia causing them to move sideways. Don't worry if this is confusing, it'll make more sense when we learn about centripetal force. But this scenario can be explained using Newton's first law of motion, and an object's tendency to move in a straight line because of its inertia. So those are examples of how we can start to apply Newton's first law of motion. Again, don't worry if any of that was confusing, we'll learn a lot more throughout the rest of this unit. In the next video, we'll learn about Newton's second law of motion and cover free body diagrams in more detail. Newton's second law is very similar to Newton's first law, but it actually tells us how the acceleration is related to the net force using numbers and one of the most famous equations in physics, F net equals ma. But that's it for this video, so let's do a quick summary. The net force acting on an object is the total or the sum of all the forces acting on it. We usually write net force as sigma F, which means the sum of all the forces. If there's only one force, then that's also the net force. If there are multiple forces, we add them together if they're in the same direction, and we subtract them if they're in opposite directions. If the forces in each direction have the same magnitude, they cancel out and the net force is zero. We say the forces are balanced if the net force is zero, and the forces are unbalanced if there is a net force in one direction. Newton's first law of motion has two parts. First, an object at rest will remain at rest unless acted on by a net force. There may be forces, but there's no net force because they cancel out. So if an object is not moving, a net force is not required to keep it at rest. It'll stay that way on its own. Second, a moving object will continue moving in a straight line at a constant speed unless acted on by a net force. Again, this could mean there's no forces on the object, or there are forces that cancel out, so the net force is zero. A net force is not required to keep an object moving, it continues moving on its own because of its inertia. If there is a net force acting on an object, then it will not remain at rest, and its velocity will change. The net force might cause the object to start moving from rest and speed up. It might cause the object to slow down or stop. Or, since velocity is a vector, it could also cause the velocity to change direction, not just magnitude. We can use Newton's first law to explain any motion that we see, at least conceptually. If an object isn't moving, then there is no net force on the object. That could mean there's no forces, which almost never happens, or there's forces acting in opposite directions that cancel out. When moving objects slow down and stop, there must be a net force acting on it, and it's usually a friction force. If there was no friction or air resistance, moving objects would continue moving in a straight line at a constant speed if the net force is zero. If an object is moving at a constant velocity, Newton's first law tells us that the net force must be zero. Otherwise, the object would accelerate. That's what happens in projectile motion. If we ignore air resistance, the only force acting on the object is a downwards gravitational force, and that net force causes the object to accelerate downwards. And don't forget that velocity is a vector, so a net force can also change an object's direction, not just its speed. Newton's first law says that an object wants to continue moving in a straight line because of its inertia. So if it doesn't move in a straight line, there must be a net force acting on the object. That's it for this video. Thanks for watching, and I'll see you in the next one.